Good morning, everyone. Welcome to the start of this next section where we're going to be talking about spectrophotometric methods. So these are going to be looking at some of the specific ways in which we can measure analytical signals. We can look at how we can use some of the information that we've learned throughout this course and actually analyze systems based on their interaction with light predominantly. We'll start off learning a little bit about how these instruments work, and then we'll talk about a little bit about how light works, and then after that we'll talk about the specifics of a few different spectrophotometric methods. Mostly we'll be talking about absorption methods, so that will focus mainly on UV vis and also on the measurement of atomic absorption and atomic spectroscopy in general. Okay, so let's get started. We classify a couple of analytical methods, classical versus instrumental. So generally, there's two main types of analytical measurement. There's qualitative and there's quantitative. The ones that we'll be discussing mostly in this class will be quantitative measurements. Whenever we meet again, if it's me teaching in third year again, we'll talk a lot about qualitative as well. So some differences. So qualitative tends to tell us what is actually present, like what molecule it is, what species it is. Quantitative generally is just looking at how much of something there is there. It doesn't really tell us enough detail to accurately say if it is molecule X or molecule Y. So some of them combine both, but like for example, infrared spectroscopy can be used for both qualitative and quantitative. However, usually even if it's like that, they end up being better at one than the other. And so that's the case with infrared spectroscopy. It's a little bit harder to do quantitative. It's definitely possible. Don't get me wrong. It's definitely possible. But it's a little bit harder than it would be usually in, for example, UV vis. So you'd only really use infrared spectroscopy if you had no other choice. Let's read this slide then. So qualitative instrumental analysis is that measured property that indicates the presence of analyte in the matrix, so the presence of some molecule. And then quantitative instrumental analysis is that magnitude of measured property that is proportional to the concentration of analyte in the matrix. So quantitative is telling us how much of something there is, i.e. the concentration. Qualitative is telling us whether or not something is present. Of course, it's not quite as easy as that. I mean, some spectrometers have prediction software. They have prediction software, but by and large, that's incredibly inaccurate. So usually we need to use our chemical knowledge and our intuition to actually assign the peaks. And this can be important, like for example, if we have a product that we're trying to bring to market or something, or some sort of new material that we're trying to understand to see its value, then and there's like some problem with it, we're going to have to do some spectroscopy and so on to try and identify what that problem is. And so we're going to have to use our chemical intuition to determine what the problem is and how we can solve it. So the species of interest then is all constituents, including the analyte, and then we often need to pre-treat this in some way. So sometimes it's not concentrated enough, or it's too concentrated, or there are interfering species. So like, for example, we might need to concentrate our sample by like removing some of the solvent. If it's water, that's pretty easy. We can just boil it off most times. Sometimes it's got like, there's 2 or 3 species, which we'll talk about chemical interference more later on, but sometimes there are 2 or 3 species which absorb light at the same wavelength or the same position as the analyte that we're interested in, and so we need to separate them somehow. Other times the species is too concentrated, so it produces like strange artifacts in our measurement. So we have to dilute in that case, but we have to take accurate accountability for each step that we do and make sure that we record the masses before and after any operations, so that whenever we go to give the final answer, we are consistent with the original system. So some classical types of measurements. So qualitative measurements for identification by color. You may have remembered like flame tests. So if you put like sodium ions in a flame, like if you just put sodium chloride into a flame, you'll kind of see it go like a yellow color. That's from the sodium. You can do it with other metals. Strontium is red and so on. Then we also have indicators like pH paper, like the red and blue one is the simplest one, but you can also have the ones that change color based on minute changes. Even just like not even the paper, just like the dropwise addition of some indicator to a beaker and then adding, I don't know, acid or base there changes the color. Boiling points, so finding out what temperature something actually boils at, and then smelling it. That can be more dangerous, but it is possible. I mean, you could smell it. That would be like, for example, like that's how you check if something is spoiled food or not. If it smells bad, I don't know, I wouldn't eat it. If it smells like it shouldn't. Then quantitative, mass or volume. So you just literally weigh it and see how much it weighs or how much space it takes up. So those are classical methods. Now we have much more advanced tools. So we still can use those. I mean, it's still good practice to sort of pay attention to like the physical sort of observations you have. Okay, well, for some reason, the species that I expected to be colorless or white is now suddenly yellow. Why is it now suddenly yellow? Or in a case that happened to me before, it was purple for some reason. So it should have been colorless and given me a white crystal. It was a purple crystal. The crystal looked right, but it was purple. So I had to remove the purple color. But after that, it was okay. But sometimes it's like that. You just need to take an accurate record of what it is you're doing in your lab manual. Then, okay, so instrumental, qualitative, so chromatography, electrophoresis, and identification by measuring the physical properties. So, for example, spectroscopy and electropotential. Then quantitative, so measuring the property and determining the relationship to concentration. So, for example, spectrophotometry, mass spectrometry, and so on. And often the same instrumental method is used for qualitative and quantitative analysis. So yeah, so that's what I was talking about earlier. You can use a lot of instruments for both. Like a UV vis spectrometer is really good for determining concentration. I mean, assuming that it has an absorption in the visible or the UV range of the electromagnetic spectrum. We'll talk about the electromagnetic spectrum later. You can still get a peak position, like a certain wavelength that it absorbs the most at, and that can be used to identify what species are present. It's not perfect, but it can be done. And usually we do keep a record of that position. Qualitative things like chromatography. So this is where we utilize the interactions of our analyte, the species of interest, with the rest of the species of interest, the rest of the solvent or whatever, because some species interact more and some interact less. So that will change the speed at which they pass through a column in the chromatography. So the column is kind of like a tube which is filled with something, which could be silica, which the sort of analyte that we put in there interacts with, and it either slows it down or it speeds it up based on its interactions. And that basically creates a separation, and so we can accurately determine which species is present. Here are some different types of instrumental methods of analysis. So we have qualitative, we have quantitative, and whether or not they're elemental or molecular. So atomic spectroscopy up here at the top, atomic absorption spectroscopy, we have qualitative, quantitative uses. So atomic absorption spectroscopy, as we'll find out later, actually totally destroys the sample that we put in. It basically burns it. into its constituent atoms. And so it makes sense that it's not very good for qualitative measurements because it tells you, well, in the sense that maybe it tells you what element you have present, but it's okay for quantitative measurement. It will tell you how much of a specific element you have. So whether that be iron, whether that be calcium, whatever it happens to be. Other things here, like for example, UV absorption. Is it qualitative in terms of elements? No, because elements don't actually participate in the UV absorption spectrum. So the only thing which absorbs are molecules or complexes. So that's why we can use it for molecular qualitative measurements, because the molecules have particular absorption points, and so that can actually be pretty accurately measured. And then the same with quantitative, how much of an element is present. No, we cannot do that. If we need to do that, a better option is atomic spectroscopy. And then, yes, it can tell us how much of a particular molecule is present, because it is molecules that we are measuring. And there's a bunch of others here, but generally we'll only be talking about UV and UV-vis spectroscopy and atomic spectroscopy. But if you're interested, you can see the others here. Gas chromatography, ICP-MS, infrared, that's a common one. Mass spectroscopy and liquid chromatography are common as well. And NMR, actually, well, all of these are common, I'll be honest. The most common, I suppose, are UV-vis, atomic spectroscopy, infrared, Raman, and mass spectroscopy, and also the different types of chromatography, like liquid chromatography. So these different measurements are making uses of different types of interaction or property of electromagnetic radiation. So whenever I'm talking about electromagnetic radiation, which we'll clarify later, I'm talking about light. Light has various different wavelengths, going from like gamma radiation through X-rays, through the visible region, up to radio waves and infrared light. But that's all part of the same electromagnetic spectrum, and it's all basically light. So different instruments make use of different properties. So emission spectroscopy, that's the kind of fluorescence, phosphorescence, luminescences, like fluorescence measurements. So it's the light which is emitted from a particular sample, as opposed to the light which is absorbed, which is the next one, which is a very common thing. So basically what happens here is we shine a light on the sample and it absorbs some of it. And then the other side, we see how much light was absorbed and at what wavelength it was absorbed. We will talk about those processes as we go through. But this is just an overview at the start, and then we'll talk about everything in more detail. Absorption spectroscopy, so we have spectrophotometry, we have photometry, we have nuclear magnetic resonance, NMR, and we have ESR, electron spin resonance. Radiation scattering, this is turbidity. This is useful in finding the size of like particles. So in like cosmetics and stuff, this is quite important to find the size of like the nanoparticles and stuff which are dispersed. A lot of cosmetics now use like finely dispersed moisturizers or whatever in a suspension of a gel or a cream. So they need to find out if everything is uniformly dispersed so that the customer or whatever is happiest. Radiation refraction, so refractometry, interferometry. So this is like useful to see how light interacts with the sample. It's not really super common. Radiation diffraction, this is common in X-ray, neutron diffraction. Don't know what happened there. And then electron diffraction as well. So these are the different types of electromagnetic radiation interacting with the sample that we're passing through. So we have X-rays interact with the electrons around an atom, neutrons interact directly with the nucleus, and electrons interact with the nucleus as well. So types of instrumental methods, we have looking at the different properties that we're trying to measure. We have electrical potential. This is potentiometry. So this is useful in using electrochemistry. So basically using electricity and chemistry to determine the concentration of something that's present, or to try and understand its electrical properties. The reason why that's important is because one of the best ways to coat something with metal is to use electricity. Electrical charge, coulometry, electric current, voltammetry, electrical resistance, conductometry. So this is like just trying to find out if it's useful for other different kinds of spectroscopy. We have mass then, so that's gravimetry. This is literally just weighing something. Mass to charge ratio, mass spectrometry. So seeing how much of a particular fragment of something is present. So for example, in mass spectrometry, what happens is that the sample gets kind of destroyed, and then we measure how much of a particular size of fragment is present. So like if it has a mass of 15 atomic mass units, we might say it's something like a methyl group, which is a carbon and 3 hydrogens. So rate of reaction then, so looking at how fast a reaction happens, so how we might measure that, so stop flow, flow injection analysis, thermal characteristics, thermal gravimetry, coulometry. So this is like, we want to know at what temperature does something decompose, or what temperature does something melt. We can measure its thermal characteristics, and then radioactivity. So different ways of measuring that are like activation or isotope dilution. That's really not that common. Like the things here that are most common that we're going to be using are thermal characteristics, mass to charge ratio, mass, and these electrical properties. Okay, so how is a basic instrument designed and set up? So there's like many or 6 different stations, I guess, within an instrument that allows us to measure our particular samples. There's the source, which produces some form of energy or mass that is relevant to the measurement at hand. So this is our light source. This is going to produce our visible light. It's going to produce our infrared light. It's going to produce our UV light. It's going to produce our X-rays, whatever it happens to be. It's all producing light, which can be a form of energy. Then we have a sample holder or cell. So this contains the sample with your analyte of interest. So this is where we put the sample before we start to measure it. There's also going to be like a sample holder, and then it's going to hold the sample there. Then we have a discriminator, which selects the desired wavelength signal from the source or the sample. So some measure or some change the wavelength before it reaches the sample, and some change the wavelength after it reaches the sample. Then after the light or energy has interacted with the sample, we need to actually try to measure it in some way. So we measure it using an input transducer, which detects the signal from the sample, source, or discriminator. So this is going to be the detector. Detectors come in various shapes and forms, which we'll talk about later. So like, for example, if it's going to be light, it's typically things like a photo tube or a photomultiplier tube, or a CCD array, so a coupled diode. So what happens is that the light has some intrinsic energy associated with it, and after it's passed through the sample, it hits this detector, and that produces some sort of like energy change in the detector, which can be detected basically by the electrical circuit which it is connected to, and then that signal, which is produced by the light hitting the detector, can be measured using the computer, and then we can get our output. Again, we'll talk about that more in detail later. Processor manipulates the signal electronically or mechanically to produce some useful value. So most of the time now we'll be looking at electronic signals, and before they used also mechanical signals, where they literally had a pen attached to a very sensitive arm bracket, which would move up and down depending on how the signal was being detected. And then readout displays the signal in some useful form. So before, this would have been a printout, an automatic printout. Now it's mostly just on a computer screen, where we can get the data as like a column of X, Y data, and we can even just print it out if we want. And so this displays the signal in some useful form. Okay, so this is kind of like what the setup looks like. So we have our energy stimulus. So this is our source of energy, passes through some analyte, which happens to be in a matrix. And then this gives us our analytical response, which is caused by the change in the energy after it is interacted with the sample. So the energy sample, say we're doing an absorption measurement, the energy before it reaches the analyte and the energy after it reaches the analyte should be different. And so that will produce an analytical response dependent on what wavelengths are interacting with the sample, because not all of them do. It's an important consideration. And then that produces an analytical response, which generally we convert into electricity. That electricity then can be passed through the circuit inside of the instrument to be recorded basically by the encoder. So the encoder records that information, and then we get the final data out. So this is a block diagram for the overall process of instrumental measurement. So an example here would be spectrophotometry. So that's going to be our UV vis measurements. We call that a spectrophotometer. We have monochromatic light energy. So we produce usually multiple wavelengths of light using just a regular bulb, or a regular bulb for this type of measurement. And then we have the analytical response, which is the absorption of light. So this is what's happening here is the light is being absorbed by the detector. Then we have a transducer, which is a photocell. So this absorbs whatever light is left over and creates the electrical signal. Then the data is going to be an electrical current, and then we'll read that using a current meter, and then the readout will be on the meter scale. So before, maybe like in the 90s or early 2000s, you would still see instruments that would just have like a little dial with a number on it. You can still kind of see those sometimes, but now most of the time, the instruments require a computer to be hooked up to them. And that's where the meter scale would be located. But before, there was like an actual like little dial which you could read. I think there are still like for UV vis measurements, you can still get that for very basic instruments. And sometimes you see in teaching labs. So basically what's happening here is that some light from our energy stimulus is being absorbed by the analyte that we're interested in. And then we're getting a response and we're converting that into electricity. And so what we're actually measuring is electricity. I know we're using light and we're sticking our sample in the light and everything involves light, but what we actually measure when it's coming out is an electrical signal. We're not actually measuring the light in any meaningful way. We're indirectly measuring the light through its interaction with the photocell, which produces an electrical signal from that light, because measuring the light itself is pretty hard to do. And it's much easier to get an electrical signal, which we can measure very well. We're very good as humans of manipulating electricity. Instruments for analysis. So data domains are the ways of encoding analytical response in electrical or non-electrical signal. And then interdomain conversions transform information from one domain to another. So this is like taking the light intensity, here. Light intensity is being then converted into a current using the photocell, and then that current is being measured using the current meter and being transposed onto a scale. So the detector here is a signal, or is a device that indicates change in the environment. So this is, in the previous example, the absorption of light. The detector is indicating the change in the environment in the sense that the light which comes out of our light source has a particular energy. And then depending on whether or not we put our analyte in the path of that light, it will absorb or not absorb the light. So if it's in the path of the light and the wavelengths match up correctly, it will absorb the light. At which point, the amount of light which remains in our beam or the energy of the light that remains in our beam will be changed at that wavelength, because some of it has been removed by the molecule. It's been absorbed. It's no longer in that, it's no longer as high energy. And so that change in energy is detected by the detector. Then the transducer is the device that converts a non-electrical to electrical data. So it's converting this light to electrical data. And then the sensor is the data that converts chemical to electrical data. So transducer is what's being used in like UV-vis spectrometers, FTIR spectrometers. And a sensor is something that converts chemical to electrical data. So that's something like like what's happening in a pH meter. They convert chemical to electrical data. So instruments for analysis. So the domain, so non-electrical domains here, electrical domains here. So non-electrical domains include physical changes. So like the color of the material, light intensity. Chemical changes are things like pH, which if we recall back to module 3, where we talked about pH being the concentration, minus log 10 concentration of the hydronium or H+ ions. Then we have scale position, so that's length, so it's literally just a position on a ruler. And then number is like, number of ions or whatever, just objects like Avogadro's number type calculations. And then electrical domains here, we have current, we have voltage, we have charge. These are all analog types of measurements. Then we have frequency, which is a time-based measurement. Pulse width, phase, these are all time-based. And then we have count, serial, and parallel. These are digital measurements. So generally what we make use of are these three here. Some instruments make use of the others. They make use of frequency as well, like an FTIR infrared measurement instrument makes use of frequency. So lagged for a moment. So the time is to vary with time. So the frequency, phase, or pulse width. So over time, the signal changes. So it may be that some of our analyte responds differently. And so some may respond immediately and some may take a couple of seconds to produce a response. So those would be time-based domains. Analog then is continuously variable magnitude. So it basically means we can like change the dial to increase, like in case of voltage, we could like increase the voltage or change the current. It's continuously variable from like 0 all the way up to 1, like 0, 0.1, 0.2, 0.3, so on. Well, it can also be smaller increments as well. Digital then, so these have discrete values. They're either on or they're off. They're either 1 or they're 2 or they're 3. They're not able to be like kind of in between those integer values. So these are the non-electrical domains. Typically, these two, physical and chemical, are the ones that we concern ourselves with the most, and some examples of those. And then the electrical domains. It's really like the important thing here is to remember that what we're actually measuring is electricity and not actually the light. We're using the light to get an electrical measurement. So here are a couple of flow diagrams of the various instruments. So here we have what it might look like to us. So we have a laser, which is an energy source. Lasers are nice because they produce very narrow wavelength ranges, as opposed to like a tungsten bulb, which produces a huge continuum of light. Lasers produce like basically one wavelength and that's it. Then we're passing that through our sample of interest, which is this tonic water. So tonic water contains a quinone, which whenever you shine a laser through it, it will turn the whole thing like a purpley blue color because of the absorption of the light by that quinone. So you can find out how much quinone is in the tonic water. Then that's what gives it the bitter taste. Then the fluorescence emission is being measured here. And then we're filtering it through this optical filter. The reason why the filter is there is kind of to remove any of the stray light which comes from the laser, because this is a fluorescence emission measurement, which again we'll talk about in more detail. But then we have a transducer, and then we have an electrical circuit here where there's a current flowing. There's a potential difference across here, the voltage. We have a resistor in here, and then here is our digital voltmeter, which is measuring the signal as electricity. Then we convert that signal into some sort of chemical measurement, some sort of value in our UV spectrum or in our IR spectrum or whatever it happens to be. Should be fluorescence emission spectrum in this case. So information flow, what's happening here? So we have source intensity, so that's from our laser. Then we have the fluorescence intensity of the analyte. Neither of these we can particularly measure very easily directly. So we need to convert them into something which we can actually read, which is electricity. So the fluorescence intensity of the analyte is converted into electrical current, which then is converted into voltage, which is then given some sort of number like here. So what laws are governing, or what rules are governing these transitions? So the source energy to the fluorescence intensity of the analyte is the laws of chemistry and physics. So the laws of absorption, Beer-Lambert law, so on and so forth. Then to convert from the fluorescence intensity to the electrical current, we have a transducer transfer function. Then we have Ohm's law, which converts the voltage into the current based on the resistance of the circuit. And then after that, we have a meter transfer function. Generally, we'll be talking predominantly only about this part, but these parts are also important, and we'll only really talk a little bit about Ohm's law, which we also kind of introduced in electrochemistry. So a general diagram of an instrument is the top one, information flow through various data domains of an instrument. This is part B here, and rules governing the data domain transformations during a measurement are shown at the bottom. So you can see that there's quite a lot going on in each instrument. Basically, as users or interpreters of the information, we're mainly only concerned with what the analyte is and the readout here. The rest of it pretty much stays the same inside the instrument. And the instrument takes care of most of the other controls, except we have to place the sample there, and then we get some measurement out at the end, and it's up to us to determine what that actually means. So the analysis concept. So what are we actually trying to do whenever we're doing analytical chemistry? We're asking three questions. We're asking what is the sample? We're asking how much of it is there, and we're asking how does it behave? So sometimes we already know what it is, but we need to confirm what it is. And then we need to know how much of it is there so that we know that the concentrations are correct. Like we wouldn't want to be putting something out to market which has too high a concentration of a particular compound in the sample, and that potentially causes a product recall or causes some adverse side effects in some customers or something like that, or it reduces the effectiveness of our material. We don't want that happening. So we have some probe, which is like, for example, the light or electrons or whatever, photons, atoms, and then we have our sample for analysis, and then we get out a response at the other end. And the probe and the response are typically the same. So if we have electrons, photons, atoms, we typically get electrons, photons, atoms at the other side as well. Typically, we measure using electrons and photons. Light is very, very good for measuring samples. So in an instrument, we have controls the applied probe and measures the system's response. So how does it control the applied probe? So it turns the light source or energy source on or off. It controls the intensity of that light source or energy source. It controls also the wavelengths which are being supplied to our analyte. And then it measures the system's response. So it measures how does the original signal and the final signal differ. Is there some absorption happening, or is there some other thing being measured? And so the physical and chemical domain is where we have the absorption of light, for example, in our UV-vis measurement, or even the FTIR measurement. It's the same kind of general principle. The energy is being absorbed by the sample, and then we are measuring how does that change the measurement. Yes, Jamin?
Sir, so a while ago, you mentioned that there would be like a laser that passes through a tonic water, right? Would the laser be an instrument or a probe?
Probe.
So what would be the instrument in that case?
The whole thing. It would be the whole thing. Going from the probe, the laser, through the analyte, through the electrical current, through to the readout that we obtain. The instrument is kind of like the overarching term for all of that.
It's like the whole system.
Yeah. It's like the whole system. Put a box around this.
So
Everything inside this box is the instrument.
so the probe is like the initial thing, the
Yeah,
first
yeah,
unit.
right, right.
Okay.
It's the thing that creates the response that we can actually measure. If there's no probe, then there's nothing happening. Yeah. The thing here though is we can change this. Like this is part of the instrument right now, but it can be removed or added. But the other things are pretty much static, especially in most like high throughput instruments. You don't really have a lot of ability to change the kind of stuff inside them. Maybe before like older instruments, you could actually like kind of tinker with them and modify them a little bit if you wanted. But now with most commercial instruments, it's quite hard to do that. And usually you need like the company to come and fix it if there's a problem. Whereas before you could pretty easily fix it yourself. I guess it's also like how electronics have moved in general. They got more complicated, so it's harder to fix them. Okay, so again, a little bit more on domains. So we have a data domain map. We have electrical and non-electrical domains. We have digital data domains, which span both. So we have non-electrical domains here at the top. We have electrical domains here at the bottom. So physical and chemical domains. So that's like pH and so on. Scale position, that's just how much of something, like what position it's on. Number, how much of something there is. Generally what we'll be dealing with and what you'll be dealing with in your future careers is the physical and chemical domain. And you'll be measuring the physical and chemical domain using the electrical domain. You might not realize it. It might not be completely obvious to you when you're doing it, but as I've tried to express here in this session, we want to measure the chemical and physical domain. It's just really quite hard. And so it's easier to measure the electrical domain, and it's also typically more accurate. And then convert that into some sort of physical and chemical domain. So there's different types. There's analog, there's time, and there's digital. Digital spans both parts of both electrical and non-electrical domains in the sense that it covers the number as well. Usually in the electrical domains, the ones which are being used the most are current, voltage, charge, and frequency. And of those four, it's current, voltage, and frequency. Frequency is used in things like FTIR measurements, so infrared measurements. Unfortunately, I don't know if we'll cover infrared measurements, but in third year, we definitely will. Physical and chemical domain is what we are actually really interested in, but it's hard to measure, so we use electricity. So data domain conversion, this is important because remember, we want to measure the physical and chemical properties of the system. However, that's hard. So what we do is we get an electrical response from that. Then we have to convert that back to our physical or chemical property. So the analyst seeks to measure physical or chemical properties of a system, and the instrument creates an electrical signal to represent the datum. So represent whatever it is that we're actually measuring. It creates an electrical signal. Data proceeds through the instrument. Different transducers convert signal from one domain to another. We saw a flow chart of that before. So we saw it going from like potential or from current to voltage through Ohm's law, or from voltage to current through Ohm's law. Analysis of the instrument behavior characterized as a sequence of data domain conversions, each analyzed separately. So yeah, so if something goes wrong with the instrument, you have to look at each one of the data domain conversions. We as users typically don't have to do that. Usually we get in like a technician or something to do that, and that's part of the process that they do. But as I said, like in the old school kind of instruments that are still present and actually still useful and still work pretty well, especially for UV vis, instruments produced like even before I was born are still probably pretty useful and pretty okay. Other instruments, like for other types of like NMR spectrometers from 40, 50 years ago, not as good as modern ones. Data proceeds through the instrument, so different transducers convert signal from one domain to another, because eventually we have to get to some sort of readout in our computer. I mean, if you think about the computer, computers are totally based on electricity. So how would that measure the number of protons which are in a sample? How would that measure light? It's entirely based on electricity, so it needs the information it obtains in electricity. And then it can convert that signal into something else, into something, a visual output for us. But ultimately, even if you just think about it like that, you're reading the data from a computer, so the computer needed it as an electrical signal. And that's where transducers come in. And transducers are what are going to convert our data from the non-electrical to the electrical domain. So the input transducer converts data from non-electrical to electrical domains. The output transducer converts data from electrical to non-electrical domain. So this is in the sense that if we have like those instruments that have like a little dial on them that tells us like a certain voltage, there needs to be like a step converter to convert the potential or the voltage inside of the circuit and convert that into an actual readout for us to read, because we also as humans are not very good at reading electrical signals, but we can read, like if it says 1.2 volts, we can read that. That's something we can do. So yeah, so there has to be an input transducer and then an output transducer. So the output transducer in a computer would be like the screen and the process inside the computer which creates the output on the screen. A thermocouple generates a specific voltage at a certain temperature. It is a temperature to voltage input transducer. So it takes the voltage and then through the, I'll show you an example of this. Like we won't talk about it in super duper detail, but we will talk about the generalities of how it works. So it utilizes the response of different metals to different temperatures, and that can produce a difference in the flow of electrons through the material, which can then be utilized to create a voltage. And then a stepper motor running a pen on a chart recorder moves the pen in a response to a current flow. It is a current to position output transducer. So this is something I talked about before. This was like in the early days, whenever even computers weren't like particularly common. I mean, the computer that we think and use of like only really started to exist like maybe in the 1970s. And even then they were pretty basic as mostly word processors and things like that. And before that, it was all chart recorder type things. So you would have some sort of motor which would respond to the electrical signal, and that movement or that response would literally draw a line on a page. So these are the kind of things that they were using back in the time of like the the famous physicists and chemists, people like I don't know, Einstein and Schrodinger and what have you. Whenever they would be doing experiments in the lab, they would literally have like chart recorders and like pens move up and down, because there was no such thing as a modern computer. They couldn't read it off a chart. They also they would have dials that would have moved up and down, but like nothing like what we have. And yet they were still able to get good information. Yes.
So the stepper motor is that like how the lie detector works? Like the
yeah, right. Yeah. That's a good
So
analogy.
it's an actual pen.
It's an actual pen, yeah. Actually moves up and down on the piece of paper. Yeah. Like the old school lie detector. That's a good one. I forgot about it. But that's basically how it works, yeah. So you can imagine like if there's a signal which is too high, the pen goes off the page and can actually break the stepper motor. So yeah, so like I mean, we're very lucky that we just get to use a computer. They had to like set up pens, make sure the pen was in the right position on the page, make sure the stepper motor was properly calibrated. It was a lot harder back then. But then things move on, and we have different concerns and problems. Now that it's easy to get information, the information that we get is more complex, and we have a harder time actually interpreting it, because we get more information. But yeah, it's basically like a lie detector, the pen on the page. So here's the thermocouple. So the temperature to voltage transducer. So yeah, that's what we talked about before. So it connects two dissimilar metals, like so. So we've got metal 1, metal 2, metal 1. So they're both connected to the sample. So metal 2 and metal 1 are connected at the same point in the sample. And we have some sort of reference material, usually like a platinum reference material, And so this has a temperature which we know very well, because if we pass a certain current or through this reference material, the platinum, it produces, like say we produce or pass 2 amps of current through our reference material. It will produce a temperature which we have recorded ad nauseum. We know the behavior of very well. And then we compare that to the sample, which is our unknown, which is our analyte, which is what we want to measure. Now we have 2 metals here, metal 2 and metal 1, which we also know very well the thermal behavior of. And so these different metals will behave differently depending on the change in temperature in the sample. And so that will create a voltage difference between metal 2 and metal 1, which will allow there to be a movement of a current or potential through the circuit, which will create a potential difference, this delta V, this potential difference, which we can actually measure between this point and this point. So the thermoelectric effect produces voltage difference, which depends on the temperature between the 2 junctions. So this one is always controlled. This one is not always controlled. So if we pass 2 amps of current through this one, we get the same response every time. If we pass 2 amps of current through this one, we get a different response every time. And so this is what we utilize to try and create this voltage difference. Basically how it works. The pH meter then is a good example of utilizing an electrical current to try and measure the concentration of H+ ions. So a pH meter is an instrument that can be used to record hydrogen ion activity, the pH of a solution. So the first transducer is a pair of electrodes, one at a fixed pH. They produce a voltage difference. So we have 2 electrodes here in our pH solution. Whenever we do it, it's usually like a pen type or a benchtop type spectrometer. So it looks like just a single probe. But within that single probe, there are 2 electrodes, which actually we talked about that in electrochemistry. Basically, they're combined together pretty nicely. And then we can measure then the potential difference between those or across those in the solution. And then using an amplifier, we're able to record how much of what the electrical current flowing through the solution is, and then based on that, we can convert that into a chemical measurement. So the first transducer is a pair of electrodes, one at a fixed pH, and they produce a voltage difference. This voltage difference then is amplified and turned into a current. This current drives a pen displacement motor on a chart recorder if we're using a chart recorder, or just uses a step function inside of the electrical circuit, which can produce an output on like a little digital dial or even analog dial, depends. And so the current drives a pen displacement motor on a chart recorder, giving a record of pH as a function of chart position, which is related to time. So this is the chart recorder that we talked about just previously. A schematic of one. So there's a pen, and paper is on like a reel, and the paper goes through, and the pen moves up and down on one axis, the XY axis. The paper moves on the Z axis, and then we get some line, and then somehow this person is able to read this as pH 4.5. Probably because there's like lines, probably like graph paper, which has got well-ruled lines. And so that's another example of an instrument, pH meter. In order to actually make these measurements, we need reference standards. So all measurement devices consist of a difference detector and a reference standard. So the reference standard is what we measure against, and then the difference detector determines the difference between the analyte, the unknown, and the standard. So we have the quantity to be measured. So this is our analyte or species of interest. And then we have the quantity of the reference standard. And then we detect the difference between those here. And then the signal is going to be the quantity measured, which is our analyte that we're interested in, minus the quantity from the reference standard. And so that will be our signal. So again, in summary for this part, the instruments measure one of 2 things. They measure the voltage, which is volts, the electrical potential across two electrodes, or they measure the current in amperes, which is the flow of electrons across some point. And that is related by Ohm's law, where voltage or potential is equal to the current times the resistance of the circuit in ohms. And what's important is that we do not directly measure absorbance, frequency, mass, concentration, or any other convenient unit. What we measure are currents or voltages, which are then converted into these convenience units. So that's an important thing to remember. We do not, using these instruments, we do not directly measure absorbance, frequency, or whatever. We measure electrical signals, either voltage or current usually. And then we convert that back. I mean, there are relationships between those voltages or currents, which allow us to convert to the convenience unit at the end, so that we get our frequencies in nanometers or wave numbers or whatever, our absorbances in the, what do you call that, in the arbitrary units, concentration in moles, so on. Yes, Jamin, sorry.
Sir, I can understand absorbance, frequency, and concentration, but how does electrical current, like voltage, relate with mass?
Oh, okay. So in like a balance, okay, I'm not, okay, I don't know exactly how a mass balance works, but whenever we measure the mass, inside there's like a little arm which moves up and down, which kind of like connects the circuit more or less, and that arm moves depending on the amount of mass that we put on the balance. And so we're, oh, I'm not very good at explaining this. I don't know the inner workings of a mass balance, but what I do know is that inside there is like an electrical circuit, which depending on how much mass we place on the top part, it changes how much current flows through the system. I think what it does is it changes how much of the resistor is like in contact with the circuit, and then that causes the amount of current flowing through the circuit to change, and then they convert that into the mass. But like, I'm not an expert on that. I just know that that's roughly how it works, and that it uses an electrical circuit. Like before, like the old school ones, they have like those big weights they put on one side, and then the other side it goes up and down, depending, and then we have to like add more weights and take them away. It's not like that. It's like a physical measurement from before. This one makes use of electrical circuits. I would encourage you to look that up though if you're particularly interested. I won't be asking you the inner workings of it. Just the thing that I want you to take away from this is that we're using electricity and not using some physical thing when we're measuring. And what I might have said there might have been totally wrong. Like I said, I'm not quite sure how the mass is measured. That's not my field of specialty, unfortunately. Sorry about that.
No problem, sir.
Okay, so sampling. So the most important single step in an analysis is collecting the sample of the material to be analyzed. So real materials are usually not homogeneous, so the sample must be chosen carefully to be representative of the real material. So this is in like instances where maybe we have a suspension of something and something else, like for example, food or cosmetics or something like that. We want to know how much salt is in our food maybe, or how much of a particular preservative is there present, which means that we need to get that in an analyzable form, because like if you just get a piece of I don't know, frozen vegetables or frozen meat or something, how do you analyze that? You have to sample it in some way. You also have to choose the part which is going to be representative of the whole sample, because like if you have a piece of food like a battered, I don't know, piece of fish or a battered piece of chicken or something, you've got the chicken meat on the inside and you've got like the breading on the outside. So how do you choose the part of that which is going to be representative of everything? So those are considerations that we have to take when we sample. A representative sample is one that reflects the true value and distribution of the analyte in the original material. So this is usually a bit easier in like pure science. Usually we deal with things which are homogeneous samples, which don't have this problem, but oftentimes like in sort of like industry or in environmental labs and stuff, you have heterogeneous samples, which are like made up of like different phases. So if the sample is not taken properly, no matter how excellent the analytical method or how expert the analyst, the result obtained will not provide a reliable characterization of the material. So like, it doesn't matter how fancy your instrument is, how expensive it is, if you don't choose the sample that you measure properly, the results that you get out of the end are going to be meaningless. So some examples of how we might do that. So for gas samples, they're generally considered homogeneous, but gas mixtures may separate into layers of differing density. Gas samples can be taken at a single point in time called a grab sample, or can be collected over a period of time or from different locations to provide an average or composite sample. So yeah, okay, that's pretty straightforward. Grab samples, yeah, you just get a liter of gas just at one time. And then the other one is like, say you've got a long pipeline, you take it at the start, middle, and the end, something like that, combine them all together, get an average sample, 1 liter from each position, and then combine them, something like that. Liquid samples can be calculated or can be collected in the same manner. So like, for example, if the local government or water company is sampling their pipelines, they could do it at different points along the pipelines. They can do grab samples at each point, like maybe on each different road, and then they can do them as composite samples where they combine all of the different roads together, or as grab samples. So you might want to do a composite sample because it could reduce the amount of replicates you need to do. So for example, they're looking to see how much, I don't know, lead is in the municipal water supply. They need to go around and check the water lines in different places to make sure that there's not too much lead, for example. Nowadays, most pipes are plastic, so you don't really get so much lead poisoning like before, where they were made of lead. So they grab the samples from each road, then they combine them all together, measure them. If the composite sample doesn't have very much lead in it, then that's good. They don't need to do anything more. But if the composite sample does have significant quantities of lead in it, then they need to go back and measure each one of the grab samples to find out which road the lead is originating from, which road maybe has the oldest pipes or whatever, and that those should be marked for replacement. Then solid samples, these are often the most difficult to sample because they're usually less homogeneous than gases or liquids. So yeah, going back to like what I was talking about with like food samples or cosmetic samples, like oftentimes it's harder to measure these because they're often not always totally homogeneous, i.e. they're not always just like one phase. Okay, so what time is it? 38. Okay, we can introduce this and we'll come back to it again next time. So talk about waves here. So we talked about light being the thing that we measure with. So spectrometric methods are a large group of analytical methods that are based on atomic and molecular spectroscopy. So atomic spectroscopy measures, which is going to be our AAS, AES, and AFS. That's the other part that we'll talk about, is looking literally at the atoms which are inside a particular analyte, a particular species of interest. And then molecular spectroscopy looks at what particular molecules or complexes are present. There need to be, for molecular spectroscopy, there needs to be bonding between the different atoms for it to be measurable. For atomic spectroscopy, there's no such requirement. Spectroscopy deals with the interactions of various types of radiation, mainly electromagnetic radiation with matter, and spectrometry and spectrometric methods refer to the measurement of the intensity of radiation with a photoelectric transducer or other types of electronic device. So that was what we covered in our overview earlier. So this electromagnetic radiation, let's talk a little bit more about it. This is the energy with wave character, and it can be characterized by using wavelength, which is lambda, frequency, which is given this letter V, and velocity and amplitude. So here is a particular, or like a sine wave, a particular wave which repeats through space. This could be electromagnetic radiation. So it starts here at the origin, and then it continues through. It oscillates in both the positive and negative parts. So it has peaks, which are up here at the top. It has troughs down at the bottom. It has a wavelength, which is the position between two peaks. So this is the first peak, this is the second peak. That the distance between those is called the wavelength. And then the amplitude is going to be the distance between the origin and the peak or the trough. And so usually with electromagnetic radiation, the peaks and the troughs have the same amplitude. So the amplitude then is the length of the electric vector at a maximum in the wave. So basically it's just the distance from here to here. Vector is just a fancy way of saying like the distance in a particular direction. Period then is the time in seconds required for the passage of successive maxima or minima through a fixed point in space. So what does that mean? It means like going from this peak to this peak. How long does that take? If we like stop it here, how long does it take before this part passes through this one? If the wave is traveling in this direction towards the vertical line, then how long does it take for this point to get to this point, which would be one complete wave? So we wait here until this point gets here, and that's our period. Frequency then is the number of oscillations of the field that occur per second and is equal to 1 over p, which is given reciprocal seconds, so seconds to the -1, or hertz. Hertz is probably the more common unit. So that's how many periods happen per second. A wavelength then, given lambda, is the linear distance between any two equivalent points on successive waves. A successive maxima or minima is given the letter of angstrom or nanometers, or well, angstrom and nanometers generally. So it's actually a length. And then wave speed is equal to v times f times lambda. So the frequency times the wavelength gives us the speed of that particular wave. So electromagnetic radiation, there's a lot of electromagnetic radiation in space, and that's why you have to wear these suits to protect yourself. Then also so they can actually move around, because there's like little jets and stuff. But anyway, that's beside the point. The reason why there's a lot of electromagnetic radiation in space is because the sun produces a ridiculous amount. We on Earth are protected by it because of the atmosphere, which absorbs most of it. But out in space, there is no atmosphere, so you're totally exposed. So electromagnetic radiation requires no supporting medium for its transmission and can pass through a vacuum, which is why another reason why this picture is here. Electromagnetic radiation is a stream of discrete particles or wave packets of energy called photons. So photon energy is proportional to the frequency of the radiation. So as the frequency changes, so too does the energy. And this is all related via Planck's relationship, which we will talk about. And it's going to be a very important relationship for this module and this part of the course. So the transmission of radiation is dependent on the medium. So whilst what I said was true in the sense that it doesn't require any supporting medium, so like it doesn't need to go through air, it doesn't need to go through water or whatever. Like for example, our voices, the sound waves, those require a supporting medium. So they can pass through the air, which is great because otherwise you wouldn't be able to hear me and I wouldn't be able to hear you. And then it can also pass through water and things like that. Those are supporting mediums. But in the case of electromagnetic radiation, light, it doesn't require that. It can pass through a vacuum, but it can still pass through other things. Like it can pass through the air and it can pass through glass. Just because it doesn't need a supporting medium doesn't mean it can't use one. So what happens here is that the radiation is transmitted through different materials, and this transmission through different materials causes there to be a change in the wavelength. So the wavelength typically changes based on the material. Now, whether it gets longer or shorter is material dependent, and it's not necessarily always obvious what is happening. Usually it gets shorter whenever you move from less dense to more dense, and it gets longer when you move from dense to less dense. So for example, in air, we're saying here that the wavelength is 400 nanometers. But then if we pass the radiation through glass, it shortens the wavelengths to 160 nanometers. So what's happening here is air is less dense than glass. So it's going from less dense to more dense. It's getting shorter, the wavelength that is. However, the frequency will not change. The frequency will still be the same. So the number of discrete waves, so from here to here, like how often does the wave pass through, will still be the same. Frequency stays the same, but the velocity and wavelength change. So it moves through the glass slower generally than it would through air, but it's still moving. Again, we'll talk about transmission of radiation in more detail shortly. Time is slow of some time. So electromagnetic waves. So we can look at the velocity of propagation. So the velocity is related to the frequency times the wavelength. So in the vacuum, the velocity of radiation is independent of wavelength and given by the symbol c. So the c is the speed of light. So c is equal to v lambda is equal to 3.0 times 10 to the meters per second, or 3.0 times 10 to the 10 centimeters per second, just different units. So the wave number is the reciprocal of the wavelength in centimeters, cm to the -1. And the electromagnetic spectrum encompasses an enormous range of wavelengths and frequencies. Spectroscopic methods are classified according to the wavelengths or frequencies that are important for analytic purpose. So yeah, so like there's different regions, like there's the UV region, there's the visible region, there's the radio wave region, there's the X-ray, gamma ray radiation, all of which can have different spectroscopies assigned to them. And generally they correspond to different processes in the physical and chemical world. So like, for example, UV and absorption is based on the energies of the electrons inside of a particular molecule. Infrared is based on the bonds which are present, like between like a carbon and a carbon or a carbon and a hydrogen. Those change the frequencies which are observed. And here we have a little number line of those electromagnetic spectrums regions. So we have here, for example, the wave number at the top. We have the frequency and we have the wavelength. These are just these can be interconverted. You can convert from one to the other, and we'll see ways which they can be converted later. So here are the different regions. So high frequency, also high wave number, is also small wavelength is the region, like for example, gamma rays, X-rays. So these are high energy regions of the electromagnetic spectrum. The shorter the wavelength, usually the higher the energy. So the wavelength here, very short, 10 to the -13, very, very small. Typically that means that they're going to be high in energy. Then moving through ultraviolet, visible, infrared. So ultraviolet is reasonably high in energy. That's one of the reasons why we need to use, like, for example, sunblock or protect ourselves from the midday sun, because it can be quite dangerous for our skin because it's quite high energy. It can cause damage to our skin cells. The visible region, then generally not that dangerous. Infrared, pretty low energy, pretty okay. Microwaves, just depends on what frequency is used there. Radio waves, not really dangerous at all. It's too low in energy. The wavelength is too long to interact with our matter. Like you're on the region here of like about 10 meters or around about 0.1 to 10 meters. So usually something is only really dangerous for biological tissue if the wavelength of that radiation is similar to the size of the particle, so like the size of a cell or something like that, or the size of a DNA molecule. That's why gamma rays do damage to DNA, because they're very, very small, and DNA is also very, very small. Ultraviolet damages skin cells because it's about the same size, or the wavelength here is about the same size as a skin cell. Radio waves, much too large. They're bigger usually, or longer usually, than a human is tall. So you can't really interact with biological matter in any meaningful way. But it can still carry information. And so radio waves are kind of the things that are used to carry Wi-Fi signals or the radio in your car, stuff like that. So you can still get a lot of information and use them pretty well. but they can't really do any damage to us. So regions are based on the methods used to generate and detect the various kinds of radiation. The portion of the spectrum visible to the human eye is tiny when compared with other spectral regions. So you can see here, visible, very, very small. It's about, I don't know what, the quarter of the size of the X-ray region, quarter of the size of the infrared region, and so on and so forth. Okay, so that'll do us for today. We'll come back to this next time. Any questions or concerns?
Yeah. Sir, I have some questions, but not related to the topic, more